Tessellated models composed of meshes are ubiquitous in many modern workflows across a myriad of industries. For example, consider the dental industry, which largely consists of organic anatomical shapes. Unlike precise, solid geometry normally seen in traditional engineering design and manufacturing applications, mesh geometry is ideal for the organic anatomical shapes encountered in dentistry and other medical applications that model human anatomy. However, tessellated models, often in the STL file format, are notoriously prone to quality problems in so-called dirty models. As a result, meshes are often corrupted, resulting in non-watertight meshes with holes and gaps. Triangle normals may be incorrect, and triangles may overlap. Therefore, the need to correct tessellated models and heal meshes is paramount. Moreover, after healing, there is often a need to edit and modify tessellated geometry like traditional solid geometry. CGM Polyhedra has robust tools to heal and modify tessellated geometry, including new functionality to fill holes within meshes, gaps between meshes, and create additional meshes by sweeping along boundaries. 3 workflows from the dentistry industry best illustrate these new capabilities in CGM Polyhedra: filling irregular holes in tessellated models of oral cavities including teeth and gums, filling concave undercut regions between the tooth and the jaw with polyextrude and sweeps, and filling the region between the tooth crown and root to create one seamless mesh. In a typical dental workflow, a patient's teeth are scanned by a handheld digital device called an intraoral scanner. The scanner optically captures positional data to render a 3D digital impression of the patient's teeth and gums. Ultimately, the impression is converted to a tessellated model and typically saved in an STL format. Sometimes, tessellated models of patients' teeth and gums have faults such as irregular, non-planar holes with missing triangles. The holes can be caused by a number of different errors, such as an inadequate scan, missing points, or poor tessellation. Fortunately, CGM Polyhedra rectifies the problem by easily closing holes and gaps in meshes. For example, consider the tessellated model of an upper jaw, including teeth and gum. The model's mesh has defects in the form of irregular, non-planar holes with missing triangles, as indicated by the open boundaries highlighted in blue. CGM Polyhedra robustly fills such holes. There are multiple scenarios in dental modeling where undercut regions between the tooth and the jaw need to be filled. For example, just leaving the concave undercut space as is and then designing tooth guides for such tooth-jaw configurations will most likely result in guide and fit issues for the patient. To illustrate this situation, consider the mesh of a molar tooth that must be affixed to the jaw mesh. In this workflow, the outer boundary or molar tooth silhouette is extracted from the mesh and projected over the jaw. Then, through a set of Boolean operations, an undercut region, also a mesh, is created between the bottom of the molar tooth and the jaw. In some scenarios, there may be a requirement to add a draft angle to the undercut. This can be accomplished by sweeping the boundary of the undercut with the specified draft angle. In this case, the top boundary of the undercut region is extracted and then projected just below it. Then, utilizing the new functionality in CGM Polyhedra, a swept region with a shallow draft angle is created around the perimeter of the projected boundary. This swept region is also a mesh and provides a smoother, more organic transition between the undercut region and the jaw. The swept region with the undercut of the tooth can be joined to the jaw by stitching, resulting in one seamless mesh. The last workflow smoothly joins the crown mesh boundary with the root mesh boundary. This is called capping because the crown caps the root. The process of capping by CGM Polyhedra essentially entails smoothly joining 2 separate meshes. Only 2 simple steps are needed to merge the 2 meshes. First, the boundaries are extracted from the 2 meshes. one for the crown, and one for the root. Next, CGM polyhedra smoothly joins the two boundaries and hence the two meshes. As a result, the crown is now smoothly affixed to the root with one seamless mesh. After capping, the resulting mesh can be adjusted. In this example, the number of triangles comprising the mesh have been reduced. Overall, the three digital dental workflows, hole filling, undercutting, sweeping, and capping, are simplified with the new functionality in CGM Polyhedra. Contact us or visit our website today at www.spatial.com for more details on the myriad of ways CGM Polyhedra can enable similar workflows in your application.